To create advanced applications, one must understand the intricacies of Spark architecture. With a firm grasp of how Spark operates, we can unlock its full potential and leverage it for more sophisticated data manipulations and analyses. So far, we've learned that data processing in Spark relies on resilient distributed datasets, or RDDs. These are crucial as they facilitate efficient data handling in a distributed environment. We've explored the creation and manipulation of RDDs, focusing on transformations like map and filter, as well as actions such as collect and count. Then, we transitioned from RDDs to data frames, highlighting their advantages for structured data operations and SQL queries. As we advance in our lessons, get ready. We're going to cover even more complex data manipulations, especially Spark's integration with machine learning and Hadoop. Now, understanding Spark architecture is essential for developing advanced applications. At its core, Spark operates on a master-slave architecture where a central driver program orchestrates distributed tasks across multiple worker nodes. The driver serves as the command center, breaking down the application logic into smaller tasks that it then schedules across the worker nodes. This design allows Spark to handle massive datasets efficiently, enabling both batch and real-time processing. Now, let's dive into implementing a code snippet that kickstarts our Spark application by creating a Spark session and loading a large dataset from HDFS. First, we import Spark session from PySpark.sql. This is the gateway we use to interact with the Spark API. Next, we'll initiate a new Spark session using the Spark session.builder. This includes setting the application name to Advanced Spark Applications and configuring the default file system to point to our HDFS instance. As we create the Spark session with .getterCreated, we're making sure that if a session is already up and running, we can reuse it instead of starting anew, which is both efficient and helps to manage our system resources effectively. Now, let's focus on loading our dataset by reading a CSV file located at a specific HDFS path. The parameters header equals true and infer schema equals true are crucial here. They tell Spark to look at the first row of the CSV as the header, giving us meaningful column names in our data frame, while infer schema equals true allows Spark to automatically figure out the data types of each column. This makes our data handling during subsequent operations a lot smoother. Now, let's see how we can improve our data frame's performance through repartitioning. The first line of code, here, demonstrates how to repartition a data frame by increasing the number of partitions to 8. This is particularly beneficial when we expect extensive transformations or shuffling to occur. By distributing the data across more partitions, we enhance parallelism during subsequent operations, allowing Spark to perform computations more efficiently. Now, once we have our data frame optimized, let me just emphasize this point. The next line allows us to validate the result by examining the number of partitions we've set. This is achieved by using the getNumPartitions method, which returns the current partition count. It's really important to monitor the number of partitions because it helps us ensure that we've struck the right balance. Too few partitions may lead to underutilization of resources, while too many could introduce unnecessary overhead. Understanding these concepts is fundamental as they directly impact the performance of our applications. Ultimately, repartitioning is a crucial step in leveraging Spark's distributed architecture effectively, paving the way for efficient data processing and analysis. Now, let's implement caching to enhance the performance of our data frame. Caching is particularly beneficial in scenarios where the same dataset is accessed multiple times, like in iterative algorithms or machine learning applications. So, in our code, we start by calling the cache method on our optimized data frame. This tells Spark to store the data frame in memory, which is designed to significantly reduce loading times for frequently accessed data. After that, we perform a transformation to filter our cached data frame, selecting only those rows where the value in a specified column exceeds 100. We use the filter function here to create a new data frame called results.df that contains just the data we want. Additionally, we're interested in particular columns, so we utilize the select method to include only the columns needed for further analysis. Finally, we display the contents of result.df with the show method, which conveniently provides a quick visual of the resulting data frame. Through caching and this selective transformation, we optimize our workflow, ensuring efficient access to large datasets while working in Spark. Now, let's dive into how to leverage SQL queries within Spark to effectively manipulate structured data. To kick things off, we need to register our data frame, which we'll call optimized.df, as a temporary view named optimized table. This step is crucial because it allows us to execute SQL commands directly on our data frame, behaving just like a traditional SQL table. And this creates a really smooth integration of SQL and data frame APIs. Next up, we're going to implement an SQL query that calculates the average of another column grouped by column name. This really showcases the powerful capabilities of Spark SQL. You see, we can use familiar SQL syntax to perform intricate data analyses while reaping the benefits of Spark's distributed processing capabilities. After running the SQL command, we'll retrieve the results using the spark.sql method, which processes our query against that temporary view we set up earlier. Finally, to display those results in a nice, readable tabular format, we'll use the show method. This combination of using SQL queries alongside data frame operations provides a lot of flexibility, allowing developers to choose the most efficient method for their specific data handling tasks. Now, let's implement a linear regression model using Spark's MLlib. To start off, we need to use vector assembler to combine our feature columns, those being feature 1 and feature 2, into a single vector column that we'll call features. This step is really important because machine learning algorithms, they expect the input to be in a specific vector format, right? So, once we've got our feature vectors set up, we can move on to training the linear regression model. We'll do this by instantiating the linear regression class, and here we specify that our features call is going to be features, and the dependent variable, our target, is defined with label call, which is represented as label column. After configuring our model, we fit it to the training data we created earlier. Pretty straightforward. Now, once we've wrapped up the training, we can make predictions. We simply call the transform method on our model using the training data as input. This generates a data frame that includes the original features, the actual label values, and our predicted values. By selecting and displaying these columns, we can really assess how well our model is performing. Comparing those predictions with the actual labels helps us evaluate its effectiveness. It's all about seeing how closely our model's predictions line up with reality. Now, let's take a look at how to evaluate the performance of our regression model using Spark's MLlib tools. We start by importing the regression evaluator, which is a super handy utility that helps us compute various metrics for our model's predictions. In our evaluation process, we'll define the evaluator by specifying the columns that hold the true labels and predictions. This is done by setting label call to label column and prediction call to prediction. Easy enough, right? Next, we'll specify the metric we want to assess. In this case, we'll begin by calculating the root mean squared error, or RMSE, by passing RMSE to the metric name parameter. Once our evaluator is all set up, we can call its evaluate method and supply it with the predictions data frame to get the RMSE value. This metric gives us insights into the average magnitude of errors between the predicted and actual values, which is crucial for understanding how accurate our model really is. Then we'll proceed to evaluate the model using R2, which is another important metric. R2 tells us how well our model explains the variability of the response data around its mean. To do this, we'll create another evaluator instance adjusted for R2, allowing us to make informed decisions about the model's quality and readiness for deployment. By analyzing these evaluations, we gain crucial insights into whether our model performs satisfactorily. Then, we'll proceed to evaluate the model using R2, which is another important metric. R2 tells us how well our model explains the variability of the response data around its mean. To do this, we'll create another evaluator instance adjusted for R2, allowing us to make informed decisions about the model's quality and readiness for deployment. By analyzing these evaluations, we gain crucial insights into whether our model performs satisfactorily. All right, let's get started. Now, let's implement the following code to read streaming data from a Kafka topic using Spark. First, we're going to kick things off by initiating a Spark session, configured specifically to handle streaming data. This step is crucial because it lays the groundwork for connecting to the Spark framework, which will be in charge of managing our data ingestion and processing tasks. Next up, we're going to create a data frame that reads data from a specific Kafka topic. Let's call it topic name. So, to connect to Kafka, we need to specify the Kafka Bootstrap servers, and in this case, they're set to localhost 9092, pointing us to our local Kafka instance. By using the subscribe option, we'll indicate which topic we want to receive messages from. Now that we've got our streaming data frame all set up, we can harness the select expert method to cast both the key and value of the Kafka messages to strings. This little casting step, it really does wonders for improving the readability of the data we're about to process. Finally, we'll leverage write_stream along with output mode append to send our processed data right to the console in real time. This means we get to observe the continuous flow of data being captured from Kafka, showcasing just how effectively Spark can keep pace with streaming information. Overall, mastering advanced Spark applications requires a solid understanding of its architecture, performance optimization techniques, machine learning integration, and real-time data processing capabilities. By strategically applying these principles, you'll enable your applications to scale efficiently while deriving meaningful insights from vast amounts of data. The world of big data analytics is continuously evolving, and with Spark by your side, you're well equipped to tackle any challenge that comes your way. As you continue to develop your skills in Spark, remain curious and innovative. Experiment with new techniques, delve into advanced algorithms, and explore the integration of other powerful tools within the data ecosystem. With practice and dedication, you'll not only become proficient in Spark, but also unlock your potential as a data scientist or engineer capable of crafting cutting-edge solutions. Happy coding, and always push the boundaries of what's possible in the realm of Spark.